In the hidden corners of our world, often just out of sight, lie landscapes that seem torn from a dystopian future. These are not natural wastelands shaped by wind and time. They are the toxic legacies of our own progress, places scarred by generations of human industry. From the sprawling grounds of abandoned mines to the runoff from smelters and factories, these sites are a testament to a time when the Earth was treated as an infinite resource and an infinite waste bin. The very soil here is a chemical graveyard, laced with a cocktail of deadly poisons. Heavy metals, the building blocks of our modern world, have accumulated here in concentrations that are lethal to almost all forms of life. Think of the grounds around old mines shimmering with an unnatural metallic sheen under the sun. The air is still, the silence unbroken by birdsong or the buzz of insects. It's an eerie quiet. Here elements like copper, cadmium, lead, and even gold saturate the earth. For most living things, from the smallest insect to the largest tree, this environment is a death sentence. But why are these metals so toxic? The answer lies at the most fundamental level of biology. These heavy metals are relentless assassins at a microscopic level. They are masters of disguise. To a living cell, a toxic cadmium ion can look deceptively similar to an essential zinc ion. Tricked, the cell welcomes the invader. Once inside, the assault begins. They tear apart the delicate membranes and machinery of cells, triggering a cascade of destructive reactions known as oxidative stress. They disrupt the function of vital proteins, the microscopic machines that do all the work, and they can corrupt the very blueprint of life encoded in DNA, causing mutations that lead to sickness and death. It is a world where survival seems impossible, a true paradox of nature where the elements we treasure for their beauty and utility are also the ones that can extinguish life in an instant. But even in these forsaken lands, life finds a way. To understand how, we must shift our perspective from the world we can see to the one we can't. Our planet is, and always has been, a microbial world. For every human cell in our bodies, there are countless bacteria, archaea, and fungi silently shaping the world around us, performing chemistry on a scale that dwarfs all of human industry combined. We may focus on the large visible life forms, the whales, the elephants, the great redwood trees, but it is this unseen majority that truly runs the show. They are the planet's master chemists and engineers. They were the first to perform photosynthesis, producing the oxygen that fundamentally changed our atmosphere and made complex life possible. They cycle essential nutrients like carbon, nitrogen, and phosphorus, forming the bedrock of every food web on Earth. Their collective impact is so immense that without them, the entire global ecosystem would collapse in an instant. These tiny organisms are also the undisputed champions of survival, colonizing every conceivable niche on the planet. We find them thriving in the boiling water of volcanic vents, the crushing pressure of the deep sea, the intense radiation of nuclear reactors, and the frozen expanse of Antarctic ice. They are the extremophiles, life pushed to its absolute limits. The secret to their incredible success lies in their genetic flexibility. Unlike complex organisms which pass genes down from parent to child, bacteria can swap useful genes with one another like trading cards. This process, called horizontal gene transfer, allows them to rapidly acquire new abilities. A gene that provides resistance to an antibiotic or a toxin can spread through a population in the blink of an eye, allowing them to adapt to new challenges at astonishing speed. It is this profound adaptability that leads us back to those metal-contaminated lands. For us, they are toxic wastelands. But for certain microbes, they are simply another extreme environment, a chemical puzzle to be solved. And among these remarkable survivors, one particular bacterium stands out, for it has solved the puzzle of gold in a way that defies belief and opens up a whole new world of possibility. The story begins not with a prospector's pan, but in the sterile quiet of a laboratory. Scientists studying bioremediation, the use of life to clean up pollution, were investigating the microbial communities in these toxic soils. They were driven by a persistent scientific puzzle. How could anything survive here? They began to cultivate the bacteria they found, but with a dangerous and counterintuitive twist. They added dissolved gold compounds to the growth medium. Now, the gold in a wedding ring is famously inert and non-toxic, but in this dissolved ionic form, gold chloride, it is one of the most toxic metal compounds known. It's a chemical sledgehammer designed to kill any cell it touches. The expectation was that nothing would survive. But as the researchers watched, something extraordinary happened. Against all odds, in a sea of death, a few hardy bacterial colonies began to grow. And as they grew, a strange dark precipitate began to form around them, a mysterious shadow spreading across the petri dish. What was it? Was it just a chemical reaction, or was it something more? Driven by curiosity, they turned to one of science's most powerful tools. Using electron microscopes to magnify the cells thousands of times, they zoomed in on the mysterious substance. What they saw was breathtaking. The dark precipitate was composed of countless tiny spheres, each one a minuscule nugget of pure, solid metallic gold. The bacteria were performing a kind of microscopic alchemy. They were actively pumping the toxic gold ions out of their cellular interior. Once outside, specialized enzymes stripped the ions of their charge, transforming them from a deadly poison into inert, harmless 24-karat gold nanoparticles that simply accumulated outside the cell. This was a watershed moment. The bacterium, later identified as Cupriavidus Metallidurans, a name that literally means metal durable, was not just resisting the gold poison, it was actively neutralizing it as a survival strategy. The gold nuggets were simply a byproduct of its detoxification process. It had evolved a sophisticated biological toolkit to survive in an environment saturated with not just gold, but copper, lead, and other toxic metals. This discovery was more than just a scientific curiosity, it was a glimpse into a revolutionary future, a future where we might harness the power of these tiny alchemists to clean up our most polluted landscapes. A future where we could develop new green methods for creating gold nanoparticles for use in medicine and electronics. And perhaps, most astonishingly, a future where we might biomine for precious metals, healing the planet rather than harming it, all thanks to a humble microbe that learned to turn poison into gold. Let us now formally introduce the hero of our story, a microscopic titan named Cupriavidus Metallidurans. Its very name tells its story. Cupriavidus for copper-loving, and Metallidurans for metal-enduring. This organism is a true extremophile, a life form that doesn't just survive but actively thrives in conditions that would be instantly lethal to almost any other living thing. It makes its home in soils saturated with toxic runoff from mining operations, a chemical soup laced with extreme concentrations of heavy metals. To survive, imagine the bacterium as a tiny fortified city. Its outer membrane is the first line of defense. To guard its gates, it possesses a set of genes known as the CCC gene cassette. This genetic toolkit codes for a powerful multi-part efflux pump, a highly specific bouncer that identifies and forcefully ejects a wide range of toxic metal ions. But the defenses aren't perfect. Some toxic ions inevitably slip into the cytoplasm. To counter this internal threat, the cell deploys special proteins known as metallocaparones. These act like an internal security force, binding to stray metal ions, neutralizing their toxic charge and safely escorting them back to the pumps for removal. This entire defensive network is a marvel of evolutionary engineering, a dynamic, intelligent survival machine that constantly senses its environment and adjusts its defenses in real time. But this microbe faces a particularly insidious threat from gold. While we treasure gold for its stability, in the microbial world, it presents a deadly danger as soluble gold ions. The inert metal we know is Au0, but when it loses electrons it becomes the highly reactive O3 ion, a molecular predator desperate to steal electrons back from anything it touches. When these gold ions enter an unprotected bacterial cell, they unleash molecular chaos. Their potent oxidative power lets them rip electrons from vital molecules. A key target for this assault is the cell's power plant, the electron transport chain responsible for generating ATP, the energy currency of life. By disrupting this chain, the gold ions effectively cut the power, quickly starving the cell of the energy it needs to live. This is the specific, deadly problem that Cupriavidus Metallidurans has solved so brilliantly. The secret to the bacterium's gold-making prowess lies in a case of mistaken identity. Copper is an essential nutrient, and the bacterium has systems to import it. Chemically, gold and copper ions are doppelgangers, similar in size and charge. The bacterium's copper import sensors mistake toxic gold ions for life-giving copper. This confusion triggers a powerful defensive pathway, deploying a specialized enzyme called copA. Its normal job is to pump out excess copper, but now it mistakenly grabs the gold ion, pulling it into the cytoplasm. Inside the cytoplasm, a different set of enzymes gets to work. These enzymes, known as reductases, are masters of a chemical reaction called reduction. They generously donate electrons to the toxic gold ion, satisfying its electrical hunger. This act of chemical generosity instantly transforms the gold ion from its soluble, reactive and toxic state into a stable, neutral gold atom, AU0. The poison is neutralized. Now the cell has a new harmless problem, a solid speck of metal it can't use, so it expels it. As more atoms are expelled, they clump together just outside the cell to form pure gold nanoparticles. The bacterium is essentially pooping out these gold nanoparticles to protect itself. The fact that this neutralized poison happens to be one of humanity's most treasured materials is a remarkable coincidence of biology and chemistry. The breathtaking discovery did not remain a laboratory curiosity for long. Scientists and engineers quickly recognized the profound implications. Instead, biomining holds immense promise for low-grade ores, a significant untapped resource. Furthermore, biomining offers a revolutionary solution for one of the modern world's fastest-growing waste streams: electronic waste, or e-waste. Traditional gold mining is notoriously destructive. Biomining offers a tantalizing alternative. The journey begins with preparing the feedstock. This could be low-grade ore crushed into a fine powder, or electronic waste shredded into small pieces. The next critical step is leaching, to gently coax the gold out of its solid matrix and into a liquid-soluble form. It is transferred to the heart of the operation, the bioreactor. This is where the bacteria get to work. They absorb the toxic gold ions from the solution and reduce them to harmless solid gold nanoparticles. The final stages involve harvesting. Various methods such as filtration, centrifugation, or flocculation are employed to separate the solid gold and bacterial biomass. The material is taken to a furnace and smelted. The intense heat incinerates the organic bacterial cells, leaving behind only the pure, molten gold. This gold can then be cast into bars, ready for use. The most profound and honestly compelling benefit of biomining lies in its potential to totally revolutionize the environmental footprint of gold extraction. For over a century, gold mining has been synonymous with cyanide, a highly toxic chemical. Spills have led to catastrophic environmental disasters, poisoning rivers and devastating ecosystems. Biomining completely eliminates the need for cyanide. By using living organisms, we replace a hazardous poison with a natural biological process, making gold extraction fundamentally safer for both workers and the planet. The biological processes also occur at ambient temperatures and normal atmospheric pressure. Conventional extraction often involves smelting ores at temperatures exceeding 1000 degrees Celsius, an incredibly energy-intensive step. In stark contrast, our microbial allies do their work happily at room temperature. This drastically reduces energy consumption, potentially slashing the carbon footprint of gold processing by up to 80%. Furthermore, biomining provides an elegant solution for the growing global crisis of electronic waste. Every year, humanity generates over 50 million tons of it, a toxic mountain of discarded gadgets. Biomining allows us to tap into this urban mine, creating a circular economy where valuable materials are recycled and reused, turning a hazardous liability into a sustainable resource. Despite its immense environmental promise, the path to widespread adoption is fraught with significant practical hurdles, the most prominent of which is speed. Compared to the rapid chemical reactions of conventional cyanidation, which can leach gold in hours, biomining is a considerably slower affair, taking days or even weeks. This slower pace directly impacts throughput, which introduces the next major hurdle: scale. To be commercially viable, a facility must operate vast arrays of large-scale bioreactors. We're talking about industrial parks filled with bioreactors the size of buildings, all requiring a significant upfront capital investment and a massive physical footprint. And inside each reactor is a delicate ecosystem. Maintaining the perfect biological conditions, a precise balance of nutrients, pH, and temperature, requires sophisticated monitoring and control systems. Any deviation can stress the microbial workforce, or worse, cause a total collapse of the culture. The very product that makes the process so unique, the gold nanoparticles, also presents a significant challenge. They are so minuscule they can pass straight through conventional filters. Separating these microscopic specks of gold from the liquid solution is a complex and delicate task, requiring advanced and costly techniques. The chemistry of the feedstock adds another layer of complexity. E-waste streams aren't pure. They're a messy and unpredictable chemical cauldron, containing other metals like lead and copper that can be toxic to the bacteria. But these challenges are not insurmountable. Overcoming them requires a multidisciplinary approach, blending chemistry, biology, and engineering. Geneticists are designing more resilient bacteria, while engineers optimize reactor designs and filtration systems. This crucial work is happening now. Pilot plants are already testing these processes, providing invaluable data and refining the techniques needed for commercial viability. Every data point collected brings us one step closer to unlocking this technology's world-changing potential. The discovery of Cupriavidus metallidurans fundamentally challenges and expands our understanding of life itself. It demonstrates that life is an active and powerful geological force. If a bacterium can precipitate gold, what other seemingly impossible feats are being performed by microbes in other extreme environments? The way it repurposed its copper defense system to handle gold is a masterclass in evolutionary efficiency, a principle known as exaptation. The same detoxification process is, at its core, an act of environmental remediation. This concept, known as bioremediation, provides a powerful and inspiring example of its potential. Scientists are now using tools like CRISPR gene editing to precisely modify the genetic code of microorganisms, potentially creating superstrains of microbial gold factories. The real frontier is to engineer microbes to perform entirely new chemical transformations, to create microorganisms that can produce a wide range of valuable substances on demand. This would not only provide a secure and sustainable supply chain, but would also be a powerful driver for a global circular economy. The future is biological, and we are just beginning to learn its language. Our journey into the world of microscopic alchemy has taken us from the poisoned soils of industrial wastelands to the cutting edge of biotechnology. This process culminates in an act that sounds like pure fiction. The bacterium excretes microscopic nuggets of pure 24-karat gold. For the bacterium, it is simply a matter of survival, a clever way to clean its immediate surroundings and protect itself from harm. It has sparked the vision of biomining, a new industrial paradigm where we might partner with these microscopic workers to extract valuable resources sustainably. The story of Cupriavidus metallidurans is ultimately a story about potential. We are only just beginning to read the library of solutions encoded in their collective DNA. Life is the most advanced technology we know. The true treasure that Cupriavidus metallidurans offers us, then, is not the microscopic gold it produces, but the paradigm shift it represents. In the quiet alchemy of a single cell, we can see the reflection of a brighter, more sustainable world, a world built on the profound and beautiful logic of life itself.